The energy dilemma. In a nutshell, the energy dilemma is a consequence of the fact that our society in the Western world has a lifestyle and a standard of living that is due to us having access to reliable and cheap electricity and energy supply. But we've also learnt that the way we've been generating electricity and energy up till now with the use of fossil fuels has also massive environmental consequences. And so the energy dilemma is really the question about how can we generate energy and electricity cheaply and reliably as we're accustomed to, and also do it in a way that's clean and doesn't have this continued and ongoing impact on the environment through emissions of carbon dioxide. My research in chemical kinetics and thermodynamics is really focused on the development of technologies to try and go some way to addressing this energy dilemma. So technologies that can help us generate energy and electricity in a way that is cheap, clean and reliable. So the reason we've generated electricity using fossil fuels in the past is because fossil fuels are relatively cheap. And unfortunately, when in the world of energy generation, cheap means polluting. So what this graph shows is a prediction of the trend in coal use for electricity generation going out to the year 2035. And what we see is in Western countries with wealthy economies, it's predicted that even though there's going to be an increase in demand, there'll be a decrease in use of coal for energy generation, and that's shown in the blue and the white sections here. And that's because wealthy countries are going to switch to more use of renewables, they're going to improve their efficiency of use and that sort of thing. But in other countries that are still undergoing massive economic development and where there's still a significant proportion of the population that doesn't have access to reliable energy or access to any electricity at all, they're still likely to choose fossil fuels as their energy source to provide as much electricity as possible to as large a proportion of the population as possible for the lowest cost. And so, I mean, that's perfectly understandable when you're talking about raising a significant number of people out of poverty. That is a priority over the potential environmental impacts of the way you do that. So what can we do about this problem going into the future? So one way is we can improve the efficiency of generation of electricity and energy using fossil fuels. We can also improve the efficiency of distribution, so how energy and electricity is transported from the generation source to the consumer. We can also improve the way that we use energy and electricity, both in residential terms and in industrial terms. We also have the option of switching to renewable or carbon neutral types of energy or electricity generation like solar or wind, wave power, or geothermal. And these technologies certainly address the requirement of being clean. Unfortunately, they're also quite expensive at the moment because they're still relatively new technologies, and also utilization on really large scale has problems because in particular solar and wind are intermittent, so they only supply electricity when the sun is shining or when the wind is blowing. Geothermal, for example, has a limited area of application in terms of geology. So they're certainly very useful, but at the moment they're not at the stage that they can provide the type of energy infrastructure that's needed on a national or a global level. And related to it is the fact that there's already a massive amount of existing infrastructure around the use of fossil fuel-fired electricity generation and energy generation. And that is not going to be switched off overnight. There are hundreds to thousands of gigawatts of electricity generation based on fossil fuels, and that cannot be replaced overnight. So there's no single silver bullet solution to this. There really needs to be a mix of solutions where renewables and fossil fuels are both utilised to address the three-pronged challenge of cheap, clean and reliable. The area of research I work on is in the development of a technology to try and make existing fossil fuel energy and electricity generation more environmentally benign, and that's through the use of what's called carbon dioxide capture and storage. So the main problem with fossil fuel energy and electricity use is the carbon dioxide emissions associated with the combustion of the fossil fuel. And the combustion of fossil fuels is for energy and for electricity is the main source of carbon dioxide emissions to the atmosphere, and the consequent impact on environment through global warming and changes in climate. So CO2 capture and storage is a technology that we basically attach to a power station. So this is a power station, we attach a CO2 capture and separation plant, and it's basically an end-of-pipe technology where we take the combustion gases that would normally be emitted directly to the atmosphere, and first we remove or separate the CO2 from that gas mixture. So it's typically a mixture of carbon dioxide, oxygen and nitrogen. We separate the CO2, return the remaining gases, emit those to the atmosphere. Now that we have the CO2 separated, we're able to compress it to liquid or supercritical state and transport it by pipeline. And then we can either utilise some of that CO2 as a chemical feedstock, for example, to make polycarbonates or to make methanol. But that's only ever going to be a fraction of the total that we separate and capture. And the rest we have to do a process called geosequestration to. And basically that's injecting the CO2 into deep geological formations that are suitable to contain the carbon dioxide for millennia. Now the advantage or the benefits of CO2 capture is that it's a process that is end of pipe. So you can put it on new power stations as well as the existing infrastructure. And it doesn't affect the reliability of energy generation. It's a technology you can turn off, turn up, turn down. The problem is, at the moment it's expensive, and it also has a significant impact on the efficiency of the power station because it consumes 20 to 30% of the electricity output of a typical coal-fired power station if you were to use it to catch 90% of your CO2 emissions. So how does capture and separation of CO2 from the gas mixture work? Well, we take our flue gas mixture of nitrogen, carbon dioxide, oxygen and pass it into a reactor vessel that contains an absorbent. And the absorbent is typically an aqueous amine solution. And the carbon dioxide, which is represented by the blue circles, gets dissolved into the absorbent and then undergoes chemical reaction with the amine that's present. Now it reacts with the amine to form carbamic acid. Carbamic acid, being an acid, gives up a proton to another amine molecule, and we end up with a mixture of carbamate and protonated amine. And if we have our absorbent at low temperature, 40 degrees for example, it's under basic conditions and it has a high affinity for CO2 absorption. Once we've absorbed our CO2, if we then pump this across to another reactor vessel and raise the temperature of the absorbent to say 120 degrees Celsius, the conditions change, and in particular the pKa of the amine changes and it becomes more acidic, and also the solubility, the physical solubility of carbon dioxide in the absorbent is reduced, and then overall the affinity for CO2 absorption is significantly reduced and carbon dioxide comes out of our absorbent, and we then have a pure carbon dioxide stream that we can then do compression, transport and sequestration to. Once we've removed the carbon dioxide, we can return the absorbent to the absorber and reuse it, and from the absorber the other thing we have is the emission of the cleaned gas, which is then emitted to the atmosphere. In reality, the process looks a bit like this, where we have columns that are filled with so there are columns that are filled with a packing material like a Raschig ring, which is a hollow ring, and the liquid flows over that from the top, and from the bottom we have the gas being introduced and it passes up through the packing material, and we have gas and liquid contacting occurring in that. And then the CO2 rich solution is collected at the bottom of the absorber and passed to the stripping column, which is at higher temperature. CO2 is released. The CO2 lean or CO2 free solution is then returned to the absorber, and our CO2 free gas is emitted from the top of the absorber. And the chemistry of absorption is really the chemistry of the interaction between the nitrogen of the amine and dissolved carbon dioxide. So this amine here is monoethanolamine, and it's the typical amine used for CO2 capture applications. And what drives the capture performance is the kinetics and the equilibria of this interaction between CO2 and the amine to form the carbamate. And also the pKa, or the basicity of the amine, is critically important because the amine has the dual role of acting as a proton acceptor. The rest of the molecule also has an impact on performance through other properties, like how it interacts with the solvent. for example water in this case, and how that affects viscosity and its heat capacity, its vapor pressure. We don't want to lose too much of it to the atmosphere. The solubility of CO2, physical solubility, is also important, as that increased physical solubility helps enhance the kinetics and push the equilibria to the products. Stability is critical as well, so degradation, thermal degradation, exposure to oxygen, oxidative degradation, and corrosion. Of course, the absorbents will be exposed to plant equipment that is made from metal for extended periods. Corrosion is also critically important. So if we have a look at how amine structure can influence performance, we can do that by making a prediction of both the CO2 rate of mass transfer, and that's on the y-axis here, and that's basically how fast the absorbent can absorb CO2, and the energy required for stripping, and that's on the x-axis, which is the energy required in gigajoules per tonne of carbon dioxide that you are able to capture. And here we have a range of different amines, going from monoethanolamine, which we saw in the previous slide, heterocycles like piperazine, through to aromatics like benzylamine, and we get a real spread of performance. And ideally what we want is an amine that moves us to the top left of this plot as much as possible, because that's the point where we have the best mass transfer, lowest energy demand, so the lowest cost and most efficient process. So we can see that the amine properties really have a big impact on how the process performs. And we also look at a few mixtures of amines here as well, because one of the routes to getting improved performance is to take an amine that, say, has good energy performance but bad mass transfer, combine that with an amine with good mass transfer but less good energy performance, and get some compromise between the two. So one challenge is to find an amine that has the perfect chemistry for this absorption process. And that, in a nutshell, is fast reaction with CO2 to form carbamate, and also basic to the point that it also takes up the protons that are released from this reaction. But the thermodynamics are also critical, because when we raise the temperature, it's the change in basicity of this amine that significantly contributes to the drop in affinity of the absorbent for CO2 and the release of CO2. So this enthalpy of protonation is also critically important, with a more negative enthalpy resulting in a greater reduction in affinity with increased temperature. Also critically important are the stability of the amine against thermal and oxidative degradation, as I mentioned. It also needs to be non-corrosive, needs to be environmentally benign, have low volatility. And viscosity is also important, because it has a big impact on the way CO2 absorbs into and diffuses through the absorbent, and also how it flows over the packing. The other area of research I focus on is finding new ways to do CO2 separation that hopefully can even bring larger benefits than, say, the incremental changes that can be achieved by just finding better performing amines. And one area I'm working on is the use of photoacids as a way to drive this change in affinity from the absorption to the desorption process. And here what we have is a reactor like before, where we introduce our gas mixture of CO2, oxygen and nitrogen. And we have our absorbent solution, which now consists of a combination of amine and photoacid. And a photoacid is a molecule that has a ground state that is either a weak acid or a base, and then upon exposure and exposure to UV visible light and excitation, it changes to a strong acid. And so here we absorb CO2 in the same way, where it reacts with the amine, but then we have our photoacid in its ground state, which is then able to act as a proton acceptor. So we end up with a mixture of carbamate and protonated photoacid. We then transport that across to our desorption reactor, where instead of increasing the temperature, we introduce UV visible light. And this results in excitation of the photoacid into its strong acid form, and it ejects a proton. And that ejected proton drives the reverse reaction and release of carbon dioxide. So it reduces the affinity of this solution for absorption, because it makes it more acidic, and then we desorb the CO2, and then we can return this absorbent to the absorber, eliminate the light, the photoacid returns to its ground state, we can reuse the absorbent. But there's still a lot of work to do around the use of a process like this. But one of the attractive features is that we don't need to use heat for the CO2 capture process. And that means it could have potential application for the removal of carbon dioxide from the atmosphere itself. And while this is not critical now, in the future, as CO2 emissions continue to increase potentially, at a certain point, if we wish to mitigate the impact of global warming and climate change to an acceptable level, we may have to start removing carbon dioxide from the atmosphere. So in the longer term, this technology could be quite feasible for that. But we still have a lot of research to do, in particular around looking at different classes of photochromic molecules, varying the substituents on the photochromic molecules to try and improve their aqueous solubility, for example, improve the lifetime of their excited state, modulate the pH range over which they function. We're also looking at using mixtures of photochromes so that we can have a few different molecules in the one absorbent that absorb different wavelengths of light, so we can utilize a broader range of the visible spectrum and improve the efficiency of the process. And we also want to look at molecules that, other than acting as photoacids, just undergo some structural rearrangement upon excitation that will switch the molecule between having a high affinity for reaction with CO2 to having a low affinity for reaction through, for example, the introduction of steric hindrance upon rearrangement, and use that as a way to drive absorption and desorption. And lastly, of course, we need to consider the issues of scale-up and reactor design if we want to implement this at full scale. So that's a bit of a summary of my research and how it relates to the big picture issues of energy and how we can produce energy cleanly and cheaply and reliably, and how chemistry is an important part of that. Thanks for listening.